Good morning, students. We are finishing our chapter differential equation today. Few sums of miscellaneous exercise are left, which we will discuss now. So, sum number 9 is given like that. Find the particular solution of this differential equation. The condition is given y is 1 when x is 0. So, the given differential equation we have 1 plus e raised to power 2x dy plus 1 plus y square into e raised to power x. So, first of all, let us write down the given differential equation in this form so that if it is possible for us to separate the variables, what we will do first, we have to think, can I separate? So here e raised to power x term is in the product with 1 plus y square term, so this can be separated easily. It is not mixed kind of term given, so we can easily separate the variables. And when I separate the variables, I am getting dy upon 1 plus y square equals to minus e raised to power x upon 1 plus e raised to power x, and here we have dx. So easily variables are separated, and now once the variables are separated, the next step will be integrating both sides. So we will just integrate, and we will get here integral dy upon 1 plus y square equals to minus sign we can keep outside, divided by 1 plus e raised to power 2x. Now this is directly formula we apply. It will be tan inverse y, and this side e raised to power x 1 plus e raised to power 2x. Now we know that e raised to power x, that means the exponent function, it does not change under differentiation as well as integration. So e raised to power x is in the numerator along with the differential coefficient of x, and e raised to power 2x we have in the denominator. So in this integral, if I just put e raised to power x as some other variable, let it be t, and the differentiation will become e raised to power x dx, it will become dt. So the whole this e raised to power x dx, it will become dt, and e raised to power 2x, if e raised to power x is t, then e raised to power 2x I will get t square. Okay, and the integral will become dt upon 1 plus t square. So again, for that we know our rule. So it will become here, I am rewriting the first integral as such. If you want, you can shift this also to the other side, and we will get here dt upon 1 plus t square equals to 0. Now when we integrate, this will be tan inverse y, and here we get tan inverse of t plus capital C, constant of integration, equal to 0, and the value of t is e raised to power x, which implies we are getting tan inverse y plus tan inverse of e raised to power x plus constant is 0. So integration is done, value is substituted back, so it is the simplified thing, and I can say this is our general solution. As we are supposed to find the particular solution at this condition when y is 1 and x is 0, so that y1 and x0 we will substitute here to get the value of this constant c. So let us substitute the values of x and y in our general solution. Okay, so general solution we have, I am shifting it here once again. So the general solution was tan inverse y plus tan inverse of e raised to power x, okay, plus c equal to 0. So here we will put y equals to 1 and x equal to 0 in the general solution. Okay, so 1 we will put here, tan inverse 1 plus tan inverse e raised to power 0 plus c equal to 0. Right, tan inverse 1 means pi by 4 plus something power 0 is also 1, tan inverse 1 again pi by 4 plus c equals to 0. So the value of c is coming pi by 2. Okay, so our answer will be, therefore particular solution will be tan inverse y plus tan inverse e raised to power x plus pi by 2, okay, not plus, I think minus pi by 2. So minus pi by 2 equal to 0, and we can simplify it. It will become tan inverse y plus tan inverse of e raised to power x is equals to pi by 2. So this should be our particular solution as the answer. Okay, so this was the simple sum just based upon variable separation method, and the next sum number 10 we will discuss now. Sum number 10 is given, solve the differential equation. We have to solve the differential equation. What kind of differential equation we have here? It is y e raised to power x upon y into dx equals to x e power x upon y plus y square dy. Okay. So if I just observe this x upon y is given, okay, e power x upon y, e raised to power x upon y. So power I have x upon y form. So the very first thing that I can think of, obviously we cannot separate the variables here. So that means it is a homogeneous differential equation. And if power is x upon y, that means anywhere in my differential equation, if I have x upon y form, I will write down the differential equation also in the form dx upon dy equals to the function. So we will simplify it. If I write down this dx upon dy is equals to, so this dy will come to the left hand side and this function will go to the right hand side. It is x e raised to power x upon y plus y square divided by y e raised to power x upon y. Now as we know, when our differential equation is of the form dx upon dy, so our substitution will become, then put x equals to vy, so that when I differentiate both sides with respect to y, okay, so the derivative of y with respect to y will be 1. It will become v plus y dv upon dy. So if I mark it as 1, 2 and 3, so from 1, 2 and 3 we can just substitute the values of dx upon dy and x value in this. So we are getting here, it will be v plus y dv upon dy is equals to, in place of x we have to put vy, e raised to power v will become, y square will come as such, y as such, e raised to power v. Okay, so I think we can separate the terms here, because y e raised to power v, y e raised to power v, it will get cancelled and we are left with v plus y upon e raised to power v, and the left hand side we have v plus y dv upon dy. Okay, so here if I just shift this v to the right hand side, v and v will get cancelled, and then y product and this term also we can cancel. So let us shift this equation to the next page. Okay, we have this thing. So when I shift v to the right hand side, it will be dy dv upon dy is equals to y upon e raised to power y. So when we just I think not y e raised to power v, I'm sorry, it will be e raised to power v. When we just transpose, means separate the variables, this e raised to power v will go to the right hand side, e raised to power dv, and dy will go to the left hand side upon y, and one y is already there. So we are left with e raised to power v dv equals to dy. Now we can integrate both sides, and when we integrate both sides, it will be integral e raised to power v dv equals to integral of dy. So e raised to power v integral e raised to power v only equals to y plus constant we will get here, and e raised to power v, the value of v, we substitute here x as vy, so the value of v will be x upon y equals to y plus constant. Integration is done, value is substituted, that's it. So this should be our general solution, or just solution of the given differential equation. Okay, so this sum number 10 was also simple. It was a homogeneous differential equation. Sum number 9 when we did it was a variable separation method based. And now sum number 11, find a particular solution of the differential equation given that, okay, we are given one condition, one hint is also given that put x minus y as t. Okay, so let us start the sum number 11. We are given here, given differential equation is x minus y into dx plus dy equals to dx minus dy equals to dx minus dy, given that we have to find the particular solution. To find particular solution when x is 0 and y is minus 1. As the hint is given, we have to put this x minus y as t. Why this thing is given? Because if you just notice here, dx plus dy and dx minus dy are given to us. I cannot separate the variables here. Okay, so let us follow the given hint and see what we are getting. Okay, so we will put here x minus y as t. Now if I put x minus y as t and differentiate, both sides, means partially if I differentiate, x will become dx, y will become dy, and this will become dt. So dx minus dy has become dt, and dx minus dy we have in our equation also. Okay, so now I think we can substitute these things which we are given here. So let us substitute. So when we substitute, I can see we have dx plus dy also, but we have the substitution for dx minus dy. So before going for this substitution, I think it is better if we just simplify our given differential equation, then we will go to this thing. We will keep it like that only because we will use it later. But let us substitute. Before substitution, let us simplify. So I am just taking my equation back. It was x minus y into dx plus dy is given equals to dx minus dy. So when I multiply, it will be x minus y into dx, okay, minus 1 dx is there, equals to, if I this keep as minus dy, and this x minus y will get multiplied here also with dy, so I can get this thing. Now one side we have dx terms, other side we have dy term. I think now we will be able to simplify it in better way. So minus sign if I just take common, I will get here x plus y plus 1 dy. Yes. Okay. So we have here, the function is given like this, one side dx, the other side dy, but when the terms, if I talk about the terms which are along with dx and dy, they are not variable separable. We cannot separate the variables here. So first of all, we can write down this thing as dy upon dx form. First of all, when I write down dy upon dx, so dx we are shifting to the right hand side, it will become x minus y minus 1 upon x plus y plus 1. Okay, so we can I hope our calculation is correct only. X minus y into dx. Okay, we have here minus dy minus of this, so it will become minus x plus y. So when I take minus sign, I should get here x minus y plus 1. Yes, so this was the mistake. We should get here x minus y plus 1. Definitely minus sign is common outside. So this is our simplified form of the given differential equation. Dy upon dx is minus sign it is x minus y minus 1 upon x minus y plus 1. Okay, now here we will use our given substitution, means our given hint. And what was the hint? Like we will put x minus y as t. Okay, so corresponding to which, if I differentiate both sides with respect to now x, okay, I will get 1 minus dy upon dx. Now why I am differentiating with respect to x? Because we have dy by dx. So if I differentiate it with respect to x, I will get the value of dy by dx. Okay, and what is that? So the value of dy by dx we will get here as 1 minus dt upon dx. Now based upon this substitution and this differentiation, our in this differential equation will get changed. We will write down from 1 and 2. Now dy by dx we will write it as 1 minus dt upon dx equals to, this minus sign I will keep as such, x minus y is t minus 1 as such, divided by x minus y is t plus 1. Now the whole function here we are getting in terms of t. We can shift this term to the other side, and we will get here dt upon dx will be equals to 1 plus t minus 1 upon t plus 1. We have just shifted this term to the left hand side and dt by dx to the right hand side. We are getting this part. We can take LCM here. We will get t plus 1 plus t minus 1 upon t plus 1. So which, that means dt upon dx, what we are getting here, 2t divided by t plus 1. Now left hand side we have dt by dx, right hand side the whole function is in terms of t, and at this particular step we can separate the variables. So we will separate the variables here, and when we separate the variables we will get here t plus 1 divided by 2t into dt equals to dx. I think you people can integrate now. This we can easily separate the terms here, and you will integrate both sides, and after integration we will substitute back the value of t, because our differential equation is given in terms of x and y. So we will bring it back in terms of x and y so that we can substitute our given condition to get the particular solution. So up to this sum part I have done. You people can complete it. Simple integration is there, just separation of terms. You just separate the terms, integrate, and you are getting your answer. Okay, sum number 12 and 13 you people will not do. Even sum number 17 and 18 also. Sum number 12, 13, 17, 18 you people have to leave, because the exercise based upon linear differential equation is deleted for this year. Now we will discuss next sum, that is sum number 14. Okay, so this is our next sum number 14. We have to solve this differential equation to find the particular solution when x and y both are 0. So x plus 1 dy by dx equals to 2 e raised to power minus y minus 1. I think in the very first step we can just separate the variables. So I am just taking my equation first of all as such. This is 2 e raised to power minus y minus 1. Okay, so we will separate the variables here, and when we are separating the variables, this term will go to the denominator. We will get here dy upon 2 e raised to power minus y minus 1, and here we will get dx upon x plus 1. Now we can integrate here. We will integrate both sides, and when we are integrating it will be dy upon 2 e raised to power minus y minus 1 equals to integral dx upon x plus 1. Right? Now this is simple. It is dx upon x plus 1. It is the linear function in terms of x where the coefficient of x is 1 only. So this will be just log of x plus 1. There is no issue. But here we will be simplifying Okay, and when we simplify this integral, e raised to power minus y is there. So this term we can shift to the either you can do one thing like means I can write it as dy. Okay, let me expound only. It will be e raised to power minus 1, and this let us write down log of x plus 1 plus constant we are getting. Now here when I take the LCM, okay, we will get e raised to power y to the numerator, and denominator we will have 2 minus e raised to power y. Right hand side is log of mod x plus 1 plus constant only. Now e raised to power y is there, and exponential function once again we know it doesn't change under integration. 2 is constant. That means if I just put this whole 2 minus e raised to power y as some other variable, e raised to power y dy, I will get minus dt. So here if you just go for this substitution, definitely minus sign will come, and I will be left with minus e raised to power y. Okay, and okay, I think better if I just do that step for you people. We will just put 2 minus e raised to power y as t, and when I differentiate I will get minus e raised to power y dy as dt. Okay, so our integral will become e raised to power y dy upon this, it will become minus dt upon t. Okay, so let me shift it to the next page. So we will get minus dt upon t, and the right hand side we already have done, it is this thing. So dt upon t, again it is log only, so we have, it will be minus log of mod t equals to log of modulus x plus 1 plus constant. Now what we can do here, log terms we can combine also, so it will be log of mod x plus 1 plus log of t. What was t? It was e raised to power, not e raised to power y, sorry, it was log 2 minus e raised to power y. This was actually equals to, we will keep, we are shifting this term to this side, so c we can take negative when I shift c to the left hand side. Log m plus log n, if I do apply the property, we will get here log of x plus 1 into 2 minus e raised to power y is equals to minus c. Okay, so now we have log and this side constant, so we can remove our log, means by taking just anti-log. If you want, you can take, when I take the anti-log, we will get here x plus 1 into 2 minus e raised to power y is equals to e raised to power minus c, which I can consider another constant as capital A or even capital C or C1 also. It is our choice. So it means this will become our the general solution. And if you people want to keep this e raised to power minus c as such, you people can do, because c is constant, so e raised to power c is also constant, no problem. Now we will put here our condition was x0 y0 in the general solution, so we will mark it as this is our general solution. When x is 0, y is 0, it will be 0 plus 1, 2 minus e raised to power 0 equals to a. So it will be 1, 2 minus 1 is 1 equals to a. That means the value of a is 1. So when I substitute back in this, so particular solution we are getting, it will be x plus 1 into 2 minus e raised to power y is equals to 1. So I can simplify, it will be written as 1 upon x plus 1. Further, if you want, you can write it as e raised to power y. If I shift this term to this side, it will be 2 minus 1 upon x plus 1, which will become 2x plus 2 minus 1. Okay, 2x plus 1 upon x plus 1. So e raised to power y, we are getting 2x plus 1 upon x plus 1, and when I just take log on both sides, so y will be equals to log of 2x plus 1 upon x plus 1. This should be our simplified particular solution for the given differential equation. If you wish, you can leave the answer here also, but by chance if they ask you to simplify the particular solution, then we have to simplify as much as we can. Okay, now this was sum number 14. Sum number 15, it is the population of a village increases continuously at the rate proportional to the number of its inhabitants present at any time. So, this sum is very similar to the sums which we have done in our exercise, I think 9.4, based upon variable separation method. And here if I take, let the population in the beginning be x, then dx upon dt is directly proportional to x. So like that only you people will do this sum, and you have to find what will be the population of the village in 2009. So you people will be able to do this sum easily if you just follow the same way as we did those sums of exercise 9.4, where principal and rate, those two sums we have done. And sum number 16, the general solution you people have to find. I am leaving this sum also for you. So sum number 15 and 16 you people can try. 17, 18 you people just cut them from your means for this year you people will not do. Okay, so with this the chapter is over and you people have to complete it properly. Thank you, students.